mass added to the system. Okay, to the system. So we know tau now is equal to what? So we go back to the problem. Tau on its when it's added with a mass is equal to 1.52 seconds. Right? So this will be equal to 2 pi. Now the mass increase. Okay, is the mass of the beam plus by the 50 kilogram, and now we divide by what? 2K. So our I should not put in seconds over here. I do apologize. So over here we will have 1.52 divided by 2 pi, and then the whole thing squared. We are going to multiply by 2K, and this is equal to m plus 50. Okay. So 1.52 divided by 2 divided by shift pi squared times by 2 is I got 117.046 times 10 to the power minus 3 K, and this is equal to m plus by 50, equation number 2. So from here, we're going to substitute equation 1 into equation 2, right? So this is equal to 117.046 times 10 to the power 3 minus 3, I beg your pardon. Small k is equal to 34.9 times 10 to the power minus 3 small k plus by, what plus? Yeah, plus by 50. Okay. So for this case, the stiffness will be equal to 117.046 power minus 3 divided by 34.9 power minus 3. 117.046 power minus 3 divided by 34.9 power minus 3. So it's equal to 82.146 times 10 to the power minus 3. And then we have 50 over here. So 50, so it's equal to 608.672. 672 Newton per meter. Okay. So the mass will be equal to 34.9 times 10 to the power minus 3 multiplied by 608.672. So 34.9 multiply by 608.672. Hey, I got syntax error. It's equal to 21.242 kilogram or 243 kilogram. Okay. So that is your answer. Are we clear? Okay. Now, in terms of weight, in terms of mass, 1 decimal point is enough. Okay. Don't go over the top. Okay. So if you put this is equal to 21.2 kilogram. You'll get full marks also. Are we clear? Okay. Because when you pee in the morning, that's 900 grams. Okay, so don't go ballistic. Yes, sir. Say it again.
Like significant figures. I'm just gonna use that for how many.
Oh, so because weights, the standard units is always in kilograms, right? So you always put it at 21.2 kilogram. You don't quote in weights in grams, right? That's a standard. Why is that? Because 1 kilogram to relate to Newton is multiplied by 9.81. Does that make sense to you? But other things, you put significant figures like this, okay, like this, okay? Right. So you can see, if you don't, now you know, if you have a system that you don't know the stiffness, what you can do. Are we clear? Okay, you let it oscillate on its own, calculate the what? You have to calculate the period. So how to calculate the period, okay? You press the spring down and let it go, right? And let it sit up and down. You time it. Then you put a known mass on top. You do the same thing. You click or you use a stopwatch to measure the period. You can get both the stiffness of the what? Of the spring and the mass of the what? Beam. Okay. I think this is pretty interesting. Or I just get happy so easily nowadays. Okay. So this is a spring in parallel. The next thing that we are going to, before I go on, any questions so far? Are we okay? Right, you guys look fresh and bright today. I hope the same can be said about tomorrow. So the next, we are going to look at spring in series. In series configuration. So the spring in series configuration, so now this is your mass. Okay, so this is your K1, this is your K2. Okay, so to determine the equivalent stiffness, okay, so this will be 1 over K equivalent is equal to 1 over K1 plus by 1 over K2. So the common denominator is K1, K2. So the K equivalent is equal to K1, K2 over K2 plus by K1. Okay. So the same, okay, I mean the same in terms of the natural frequency, okay, or I will write this out, the undamped natural frequency omega n is equal to square root K1, K2 over K2 plus by K1 and then brackets, close bracket, multiply by F. So likewise, the period of oscillation tau is equal to 2 pi over omega n. So we have 2 pi over here, the whole thing square root m K2 plus by K1 over K1, K2. Okay. So we'll quickly look at the next example. Okay. So example number 3. All right. We have a system that a spring are in series and then attached to a mass M. Okay, so K1 is equal to 1,500 Newton per meter. K2 is equal to 1,000 Newton per meter. Okay, And we have a mass. Mass, for this case, is equal to 20 kilogram. Okay. So we are going to determine the equation of motion. Okay, we're going to determine the equation of motion, and given when time is equal to 0, okay, x is equal to 0. When time is equal to 0, x dot, which is equal to your velocity, is going to move downwards by positive 6 meters per second. So we are going to declare that going down x is positive. Okay, when I declare x is positive, going down does not mean there's a force vibration. There's no force applied. So i.e., so when I have a structure, right, what I'm going to do is I'm going to let my hand move and contact this weight by 6 meters per second. Once the 6 meters second is there, okay, transfer to the load, my hand will go off. Are we clear? Right? You have to visualize it in this way. Don't just, mathematically it's like, but what does it mean physically? So my hand is moving at 6 meters per second, transmit to the load, assuming full transmission, the load will move by 6 meters per second, and that's how it's going to what? Oscillate. My hand will not stay on the what? On the mass, okay, because it is a unforced system. Okay, when it's a forced system, then it's different. My hand will stay on the mass and have a sine or cosine oscillation. Right. So we are going to determine the equation of motion, and some of you, by Eugene, what do you mean by equation of motion? So the equation we're going to determine at the end of the day is able to determine the signature of time and displacement. Okay. So from here, we know that the spring is under series configuration. All right. So we know that the K equivalent will be equal to K1 multiplied by K2 over K2 plus by K1. So we just plug in the numbers for now. So 1,500 multiplied by 1,000 divide by 1,000 plus by 1,500. So this will be equal to 1,500 times by 1,000 divided by 2,500. So this is equal to 600 Newton meter. Or Newton per meter. Okay. So we know for a system like this, there is no damper, right? So we are aware that the general solution for undamped free free vibration. So we know that the expression over here is x as a function of t, and then this will be equal to C1 cos omega nt plus by C2 sine omega nt. So we know that omega n is equal to square root of your K equivalent over your mass. So this will be equal. So our K equivalent, which we have found, is 600 divided by the mass of 20. So 600 divided by 20. Square root the whole thing is 5.477 radians per second. Okay, 5.477 radians per second. So when we substitute to the equation over here, x as a function of time, so this will be equal to C1 cos 5.477 t plus by C2 sine 5.477 t. Okay, so we are going to substitute to our first boundary condition. We're going to substitute. So I'm going to call this our equation 1. So we're going to substitute when x is equal to 0, time is equal to 0. So for this case, C1 into equation 1. Okay, so we know therefore C1 will be equal to 0. Okay, then we're going to substitute x dot is equal to 6, right? When time is equal to 0. Okay, but before we're going to substitute the second boundary condition, we know that x dot is equal to minus C1, right? Multiplied by 5.477. Hold on, I better write properly. Minus C1, right? 5.477 sine 5.477 t plus by C2, right? 5.477 cos 5.477 t. We know C1 is equal to 0, so this expression is equal to 0. So this is going to be 6 is equal to 5.477 C2. And then you have cos of 0, which is equal to, why cos of 0? Because time is equal to what? 0. So therefore, C2 is equal to 6 divided by 5.477 is equal to 1.095. So finally, from here, x as a function of time will be equal to 1.095. And it will be sine 5.477 t, and the units will be in meters. I'll see you guys tomorrow. Yes.
What you write the general solution?
No, general solution will be provided. Don't derive the general solution. I'll see you guys tomorrow at 4:30. Same place.